Welcome all. Today we will take up the topic modes of data transfer between the central computer and input output devices. So, how can we transfer the data between these two things, whether from this to this or this to this? What are the various modes of data transfer? We should remember that when our data comes from an input output device, it ultimately goes to the memory. Or if the data has to go to the input output device, it comes from the memory. So the ultimate source and the ultimate destination of data is within the computer is memory. It is not CPU. CPU may help in the transmission of data, but it is not the actual source of data, nor is it the actual destination of data. The data transfer can happen between a central computer and IO device in three ways. One way is called programmed input output. The second is called interrupt initiated input output. And the third is called direct memory access, or famously known as DMA. So, the first we will take programmed input output. As the name tells us, it means an input output transfer where there is a program involved. So that means there will be a program which will be run, which will be run by whom? Obviously the CPU. The CPU will run a program to transfer data between the computer and IO device. The program will uh, be made up of obviously instructions, and those instructions of the program, what will they do? They will first transfer the data from the IO device to the CPU, then from CPU to the memory. Or it may be the other way, from memory to CPU, then from CPU to IO device. So CPU exists as an intermediary which transfers the data between memory and IO device. In this in this concept, the CPU has to continuously execute a program to check the status of interface registers. Since this is a programmed input output, the CPU will have to continuously run a program which will check, what will it check? It will check the status register of interface units. So an interface unit has a status register. That status register tells us the status of input output, whether data has been sent or is to be sent. So that status register needs to be continuously checked. So how will we check that using a program? But in this programmed input output, the computer needs to continuously run these instructions, this program, which will check the status of the status register. Then only will the CPU come to know whether a keyboard wants to send the data or it does not want to send the data. So it has to continuously check the status of the status register. This method is obviously problematic in the sense that it keeps the processor needlessly busy, because if you have to transfer data, the time taken for data transfer is fine, but the time to continuously run that program, maybe it may take many milliseconds, many nanoseconds. You have to continuously run that program, and after that there will be a transmission that may be of 10 milliseconds. So it may happen that you have to run the program for 100 milliseconds, then data will come for only 10 milliseconds. So obviously it keeps the processor busy, needlessly busy. So this concept, programmed input output, is usually used in those computers that are dedicated to monitor a device continuously. If there is a device, we have to continuously check it, continuously keep a check on it, then this method is okay. This is a diagram which is showing us data transfer uh, from IO device to CPU. So this is some IO device, for example, a keyboard or a printer. This is the CPU, and in the center there is an interface unit. We know that on one side there is an IO device, another side CPU, and there must be an interface unit in between which will help in communicating these two things. So this diagram shows how the programmed input output will happen. We know about this thing. This is handshaking. So we have learned about this thing, how this handshaking concept is done. So by handshaking, the input output device, for example, may send a data here, but the CPU has to continuously read the status of this status register. So there may be a flag bit in this. If this is on, that means data has come. If it is not on, that means data has not come. So whether this is set or it is not set, it is to be continuously checked by the CPU. So if I say that a CPU has to check the contents of a register, how will it do that? First, it will transfer the contents of this status register to the CPU. Then here an if operation will be performed to check whether the bit is set or it is not set. So before transmission, after every few nanoseconds or milliseconds, this register has to be taken here, and then here an if operation has to be performed to check whether this bit is set or not. And when this is set, only then the data from this data register will be transferred here. Otherwise CPU has to wait. So this thing can be summarized in a flow chart here. The flow chart says that read the status register. That means the CPU, after every few milliseconds, will take the contents of the status register and move it to the CPU. And this operation obviously will be called a read operation. So after this read is complete, then the CPU will check the status of the flag bit. If the flag bit is 1, that means the keyboard or some other device has sent some data. So if it is 1, then that means the data in the data register is valid. Now the CPU will do the actual thing, that it will take the data from the data register, it will read that, and then after reading it, it will store it into memory. So whole reading is complete. The operation, if the operation is complete, obviously it is here. If only one transmission has to be done, only one byte is to be transferred, then it is complete. Then the program will start. And if it is not complete, if more bytes are to be sent by the keyboard, then this will again start. Now Coming to the second way, this is called interrupt initiated input output. In the earlier method, programmed input output, there was a clear problem that the CPU was kept needlessly busy. So the concept says, now this concept says, why not to do one thing? Whenever the keyboard wants to send some data, it will put on the flag register. When the flag register is set, a signal automatically goes from the interface unit to the CPU, which tells the CPU that some data is coming. So the CPU does not have to continuously check the contents of the flag of the status register. It is the interface which will automatically pin the CPU. It will tell the CPU that some data has come. This way is called interrupt initiated input output. That means whenever some data is coming, an interrupt signal will be generated. This interrupt signal will go to the CPU. It will interrupt it, means that the CPU will be doing some other execution of some other program. It will interrupt the CPU, will tell the CPU that some data wants to come. The CPU will stop the execution of the current program and will move to the execution of this reading. So when this will happen, three steps will be there. So what will be the first? This, when an interrupt comes, the first thing CPU does, it stops the execution of the current program which it is executing. Then, since it has to go to another program for reading, it will save the address of the current program where it has left. So it will save the return address in a stack. So because it was already executing a program, for example, it has already executed 5 steps in this program. Now the sixth address of the sixth step will be stored onto a stack. Why? This is only for memory remembrance purposes. So when the input output operation will be done, processor has to come back and start from the sixth line. So he will take the address of that sixth line from the memory stack. So this is an important step. Before leaving the current thing and going to a new thing, computer will store the contents, store the address of the current thing, current next thing into stack. So the address of the next instruction will be in PC, in program counter. That program counter contents will be stored onto a stack. So I am simplifying things here. I am saying that there is only an address that is to be stored onto a stack. Usually there is not only an address, there will be other things also related to the program that may be stored on the stack, which include address, and that is called a word. So for the time being, let us suppose that only the address of the next instruction would be stored on the stack. Then after this thing, the computer will start to run another program, another function. A routine means a function, another function that will be used to do the input output transfer. This function is usually called service routine. So routine means function, service means something is to be serviced. Serviced means that there is an input output operation. So this terminology, service routine, means a function that is used to input, for inputting or outputting something. That function is called typically a service routine. This interrupt initiated input output is of two types. One is called vectored interrupt and another is called a non-vectored interrupt. These types, this categorization is based on the address to which it has to go. So here you can see the computer stops the current program and goes to a new program. When it branches to a new program, new routine, new function, so this function obviously have some address. So what will be this address? This address, what type of address it will be? It may be of two types. Either it will be a vectored address or a non-vectored address. Vectored address, so here is a mistake in this presentation. I have made a mistake here. This is non-vectored and this is vectored. So in a non-vectored interrupt, the address, the branch address will always be a fixed location in memory. It will always be a fixed location in memory. So there in memory there will be some location where there will be a routine. That routine is used for input output operation. A program or a function that will be used for input output operation is somewhere in the memory at a particular location. For example, it is on 50 location. So this 50 will always be there. The same address will be always there, 50. So this is called a non-vectored interrupt. This is vectored interrupt. Vectored interrupt means where the address is given by the source. The thing, the interface which is creating the interrupt, it will itself give the address of where to go. Where is the service routine? So what is the address of that service routine? That will be itself given by the source of interrupt. So that is why it is called a vectored interrupt. That means it has an address with it. And this is called non-vectored. That means it doesn't have any address. There is a fixed address in memory. Whenever there is an interrupt, input output interrupt, computer goes to that 50 location, for example. Here the location may be different. So this type of branch address is called interrupt vector, because this is a vector. This gives us an address of an interrupt. Again, the interrupt vector may be direct or it may be indirect. So what is a direct interrupt vector? Direct interrupt vector means where the address of the service routine is given. Means if the address there is written in this address, this vectored address is 1000. If you go to 1000 in main memory, you will find the service routine. Indirect means if you go to that 1000, at that 1000 there will be the address of the service routine. Means at that 1000 location, you maybe there will be written 5000. So the actual address of the service routine is 5000. This is called indirect address. Now, since interrupt way is a better way than programmed way, but there is one issue that interrupt may be generated by many input output devices at a time. If more than one input output devices generate an interrupt at a time, what will happen? Say for example, a scanner and a keyboard simultaneously want to send data to the computer. So what will happen in this case? There will be a conflict. So the computer has to do something. Either it has to make some algorithm, use some algorithm, or do something with the hardware in a way that a priority will be kept. A priority will be introduced, which to service first and which to service second. So for example, if the hard disk wants to, if the magnetic disk wants to send data and at the same time keyboard also wants to send data, so there must be a priority, who is to be given higher priority and who is to be given secondary priority. So obviously in these two it should be the magnetic disk which should be given more priority. So how to give this priority thing? So there are two ways, software way and a hardware way. So priority interrupt means when you have to establish a priority on interrupts, which interrupt has more priority. If we adopt a software way for priority, this thing is called polling. And if we use a hardware method to solve this interrupt, simultaneous interrupt problem, then that method is called daisy chaining. Let us see them one by one. Polling, it is a software based method. In this, there is a common branch address for all interrupts. That means whenever an interrupt occurs, the branch goes to a common address in main memory. What is at that address? At that address, there is a routine, a program that does the polling. That routine can be easily understood by that thing which we study in programming called if else. So in that program will be written, obviously if the interrupt is from magnetic disk, fulfill this request, start that read from magnetic disk. Else if the interrupt is from keyboard, start that thing. So because of the if else, obviously the magnetic disk will have more priority than keyboard. And if there is another device C which has a lower priority than keyboard, then below there will be again else if the device is C, then it will be addressed. So if else statements will be kept in a particular program. This program will do the polling. That means it will decide which one to address first and which one to address second and which one to address third. So the thing which has the highest priority, that will be first, second highest second, third highest third, and so on. But this is the software method which is called polling. This polling has one disadvantage, that it is slower as compared to hardware method. Why slower? Because to do this thing you have to run a program. So that means whenever an interrupt comes, there might be a program, there will be a program that is continuously to be run. So this running of program takes extra time. So another way to solve this interrupt, simultaneous interrupt problem, will be a hardware method. So that hardware method is called a daisy chaining. The hardware method for doing this priority interrupt thing is called a daisy chaining. This is a very simple method where you have to just put the wires in a particular way between the CPU and the IO device, and it will automatically become a priority interrupt thing. Here, this diagram summarizes the concept of daisy chain priority interrupt. So we have three devices. For example, this may be magnetic disk, magnetic tape, then keyboard, and all are connected to the CPU. Data transmission is to be done between these things. These are IO devices and this is the CPU. The IO devices produce interrupt whenever they need, whenever they need to send data, for example. So this thing goes to the interrupt. So this is INT, means interrupt. So interrupt is generated by any one or more than one at a time. This here negative logic or operation is used here. So what does that mean? That means here that is equivalent to that it is here a NOT gate and NOT gate here and NOT gate here. Then all three go into an OR gate. This is called a negative logic OR operation. So that means one more thing, that whenever this is 0, that means it is producing interrupt. Whenever this is 1, it means it is not producing interrupt. So what will happen by this negative logic? Or if any one of these or more than one is 0, then an interrupt will be produced automatically. For example, if this is 0 and this is 1 and 1, fine, 0 by NOT gate becomes 1, this becomes 0, this becomes 0. So 1 0 0 in an OR gate produces 1. In the same way, if two devices at a time become 0 0, both produce interrupt, so again this will become 1. So whether one will produce interrupt or many will produce interrupt, negative logic OR will create a 1 here. So an interrupt signal will be sent to the CPU. So for the sake of argument, let us suppose currently this and this has simultaneously produced interrupt. So this will become 1 and CPU will come to know that interrupt has occurred. In response, the CPU will give an interrupt acknowledge, INT ACK. Interrupt acknowledge will be produced. This interrupt acknowledgement, the wiring is done in such a way it will go here. So what will happen? This device will get an interrupt acknowledge here, PI. PI means priority in, PO means priority out. So the interrupt acknowledgement comes here, 1 comes here. Whenever there is 1 here and there is 0 here, means that this device has produced an interrupt and it is also getting an acknowledgement. When there is a combination of this thing, then this device will start its own routine. Means reading of this device will happen. The reading obviously will be done by a routine. Routine is a function which will transfer the data from here to here, from here to here. So that routine is at this address. VAD means interrupt vector address. So this device will say that this is the address of that program, of that function which will transmit data from here to here. So once the transmission has been done, this will put off its interrupt signal and will put 1 on this PO. 1 on this PO means that I don't now have any interrupt. You can continue further. When it was having an interrupt, it was 0 here, and when this is done, it will put 1 here, this 1 here, and if this device has produced an interrupt, which means here it will be 0 here, this 1 and 0 combination will do the servicing of this device. And if this device has not produced an interrupt, it will forward this 1 to here. So this will service itself. So in this way, whenever there is simultaneous interrupt, it will be the highest priority device, this one. The organization of these devices is done in such a way that the highest priority device is here, second highest is here, third highest is here, and so on. So always and always the highest priority will get the servicing first, then the next priority will get servicing, then the next will get servicing, and this will happen in this way. So automatically by this organization of hardware, daisy chaining method will be executed. Let us try to solve this numerical problem. It says that we have a FIFO buffer. So buffer a register which is stores some data temporarily. FIFO means first in first out, which means that this in this buffer the first thing that comes into it is the first thing that goes out. So this buffer uh, has many locations in it to store data. So it is not a single register buffer, it will have many registers, many storage locations. It can store more than 1 byte. So information is inserted into this buffer at a rate of m bytes per second. So in 1 second, m bytes are inserted into this buffer. Means m entries are made in this buffer in 1 second. And the information is deleted at the rate of n bytes per second. Means in 1 second, n bits are removed from this. M are added, n are removed, n bytes. And what is the maximum capacity of the buffer? It is k bytes. Now a part says, how long does it take for an empty buffer to fill up when m is greater than n? So this buffer, which has size k, is initially empty. Then how much time it will take to fill it completely to k bytes? Given is that m is greater than n. What is m? Number of bytes added per second, and number of bytes deleted per second. So a part, size of FIFO buffer is k bytes. Bytes inserted into the buffer in 1 second is given as m. Bytes deleted from the buffer in 1 second is given as n. This a part says that m is greater than n. That means number of bytes added to the buffer per second are greater than the number of bytes deleted from the buffer in 1 second. That means in total there will be an increase in the number of bytes. So that implies net bytes added to the buffer in 1 second will be m minus n. M are added, n are deleted. M is greater than n. So how much will be the total increase? It will be m minus n. So now this is very easy. If in 1 second this many bytes are added to the buffer, how much time it will take to fill the whole buffer which has size k? K divided by m minus n. This means that, for example, if the size of the buffer is 10 and m minus n, 3 things are added in 1 second, 2 are deleted. So that means in 1 second the total addition is 1, 3 are added, 2 are deleted, means the total increase in 1 second will be only 1. So how much time it will take to fill the whole thing? 10 divided by 3 minus 2, that will be 1, which means 10 seconds. Obviously, if one thing is added to a buffer per second, it will take 10 seconds to fill that 10 slots in the buffer. Let us move to second part. How long does it take for a full buffer to empty when m is less than n? So things added per second are less than things deleted per second. So he is saying, you suppose that the buffer is full. So how much time will it take to uh, empty this buffer? So obviously, if m is less than n, net bytes removed from the buffer in 1 second will be n minus m. N are removed and m are added. Net removal will be n minus m. So how much time will it take to empty the buffer? It will be k divided by the total removals, k by n minus m seconds. So this means that if the buffer is of size 10, for example, and 3 things are removed from the buffer, in 1 second, and 1 is added. So 3 minus 1 means 2. So that means obviously 5 seconds. In 5 seconds, it will be empty, because in every second, net 2 are removed. Out of 10, if 2 are removed in 1 second, so in 5 seconds, it will be empty. Coming to the third part, is the FIFO buffer needed if m is equal to n? That means number of bytes added and number of bytes removed is same in 1 second. So if I add one thing, immediately that one thing is removed. So there is obviously no need of a buffer then, because buffer is something related to storage. In this case, we don't have to store anything. That one thing is coming, that same thing is being removed at the same time. So when m is equivalent to n, so we don't need any buffer. So is the buffer needed? No, we don't need this.